All right, good morning, you guys. Today we are adding one more layer, and what's so crazy is this is our last real layer. We're going to be in practice mode after today. So first off, we're just talking about concept. So interpreting the p-value, the probability value. So we really think of it as a conditional probability. So if I return to what is a conditional probability, that's when we are saying, okay, it's really both over the given. We're picking from a subgroup within a larger distribution. So here we're saying, essentially, we see, what is the likelihood that we see our observation what is the likelihood we see our statistics, specifically our observation, given that the null hypothesis is true. Okay, so again, we're thinking about it as what's the likelihood that we're seeing our statistic, we're seeing our observation, if we're working under the assumption that our null hypothesis with that stated parameter as the mean, right, is true. So there's really two types of conclusions that you can make, right? We know that we are totally contingent on what the alpha level, the significance level is, and then if our p-value is smaller than that threshold, we reject the null hypothesis. We think there is convincing evidence for the alternative, and then we just add our context. If the p-value is larger than that threshold, we fail to reject the null hypothesis. We say there is not convincing evidence for the alternative. But I want to add here that, again, this is all contingent. It all relies on the alpha level. I could also call that the significance level. Okay, so example 1. Rob once read that 1/4 of all people have played or danced in the rain at some point in their life. So that part seems important. 1/4 of all people. So that's telling us the parameter of 25%. His friend Justin thinks that Rob's value is too high. Doesn't think that's true for their high school. It's too high. To settle their dispute, they ask an SRS of the students in their school and find that of the 80 students who are surveyed, 12% have played or danced in the rain. Assume an alpha level, significance level of 0.05. Okay, so here, if I just first break it down, my sample size would be the students in the school, 80 of them. P is the 1/4 who have played or danced in the rain, and the complement would be the 75% who have not. So when I first write out my hypotheses, my null hypothesis, right, maintaining the status quo, we have the p, the parameter, set at 0.25. So the alternative, we got to read this next statement real clearly. Justin thinks Rob's value is too high. So he's saying that it's got to be less than 0.25. Just underline that part right there. So here we go. The null hypothesis is maintaining the status quo. And the alternative, we're saying, well, that figure's too high. It must be less than the 25%. So now, interpret the p-value, the probability value. So p, my parameter, is 0.25. Okay, that's going to be the mean that I'm building my distribution around. My statistic is the 12 out of 80 who were surveyed and played and danced in the rain. So that would be 0.15. That's the statistic that we're coming up with. Our standard deviation, big square root, P times Q divided by N, which is 80. Okay, so square root of 0.25 times 0.75 divided by 80, and that gets us about 0.0484. Okay, take it to the normal curve. So right here, right smack in the middle, is the parameter, the 0.25. I'm assuming that this is true. Here would be my 0.15, and I'm looking at that lower tail. So here's my negative infinity, or negative 9,999. So take it to my normal CDF from negative 9,999 up to 0.15. My mean is 0.25, my standard deviation of 0.0484. So when I crunch all of that, I'm going to get 0.0194. So that is my probability value, right? Building off of my true parameter of 0.25. So I'm assuming that this is the true parameter. So I'm saying how likely or unlikely is this result over here? Keep in mind that our threshold up here was 0.05. We are coming underneath that value. So again, if I just put this into words, right, if we're assuming that this is the true parameter, so if we assume that the true parameter of people who have played Danced in the Rain is 25%, then there is a 1.94% chance, right? That's coming from right here. Of getting a result or a statistic of 15% or less in a random sample. Okay, so again, I'm just trying to really flesh out what that p-value represents, the probability value. So we're saying if we're building around this mean right here, this is our true parameter. If we assume that that is true, how likely is it that we're getting this outcome? So assuming that this part is true, then we only have a 1.94% chance of getting this statistic or less in a random sample. So pretty unusual. So state the conclusion in context. We're saying, okay, it's so small. The p-value, probability value of 0.0194 is small. Right? And really we're going back to that alpha level right here that we set. It's smaller than the 0.05. So lower than that alpha level of 0.05. So since it's lower, we're saying, this would be super unusual. We don't think that we're maintaining the status quo. So we're going to reject the null hypothesis. And then instead, that means that we are ruling in the alternative. We think that there is evidence that less than 25% of students at Rob's school have played or danced in the rain. So we conclude that there is sufficient evidence that less than 25% of students at Rob's school, I'm just going to keep it short and sweet, so of students have played or danced in the rain. All right, so again, I've always wanted you guys to be strong in concept. So here, just making sure that when you solve for the p-value, it is a probability. It is the likelihood of this scenario playing out if we are assuming that our null hypothesis is true. So we're seeing a probability that is less than the threshold that we set with the alpha level. So we're saying that this result is so unusual, we don't think the null hypothesis is true. We're going to reject it, and then in turn, we're going to argue in favor of the alternative. We think that there is sufficient evidence of the alternative right here, that less than 25% of students have played or danced in the rain. Okay, a little bit more with the alpha level, and then we're going to talk about some errors in a very general way. So we need to make a firm decision about whether or not to reject the null hypothesis, right? And that's why we have an alpha level. When the p-value is small, again, I just want you to think of this as the probability level, because we start to see a lot of words that have p's in them. So the p-value is the probability level, or probability value. Okay, it tells us that our data is very rare given the null hypothesis is true. So when it's small, we're saying, this is so unusual, this is so rare if the null hypothesis is true. So when our probability value, when our p-level, or p-value is less than the alpha level, then the results are statistically significant and we can reject the null hypothesis. So common alpha levels we see are 0.05, 0.1, and 0.01, which really, if I write those as percentages, would be 5%, 10%, and 1%. So this is what we see most common. So it just depends on what threshold we need to set. So if I was doing like a medical study, I might set my bar here, it might be stricter and set it at 1%. We see that the 0.05 is the most common, that 5%. And one thing that I just want to point out to you, I'm not sure if I'll have time to go deeper into this, is that these numbers are really the complement of the confidence level. So complement of the confidence level. So if I was looking at a confidence level of 95%, right, this is its complement right here, 5%. That 5% of the time that we are off target, that we miss target. Okay, we use an alpha level based on consequences of an incorrect conclusion. Those incorrect conclusions are our type 1 and type 2 errors. So a type 1 error is a false positive. It means that our null hypothesis is true, but we reject it. A type 2 error would be a false negative. The null hypothesis is false, but we don't reject it. So here, a good example that we always give is we go back to the legal system, and we think about a court case. So let me write this out. So here would be a court case. I'm going to think about what would our null hypothesis be, what would be our alternative hypothesis. So our null hypothesis, right, we always assume not guilty. Okay, and then our alternative would be guilty. So if I'm thinking of a type 1 error, right, that's our false positive. This is how I like to visualize it. I'm going to draw an arrow here to here. This is the truth, but this is what we actually found. That's our false positive. So you are actually not guilty, but you were convicted anyways. All right, you are not guilty, but you're still convicted. That's a false positive. You were falsely found guilty. Okay, a type 2 error is your false negative. So I'm going to draw my arrow here to here. So this is the truth, but where my arrow leads, that's what we actually found. So the truth is that you are guilty, but you were found not guilty. So you are guilty. So that's the truth. You are actually guilty, but you are not actually convicted. Okay, so this little system up here I think is super helpful. This right here is the truth, and where the arrow leads, that's what we actually found. Over here, this is the truth. Where the arrow leads, that's what we actually found. Okay, and I have a little chart. You can break it down and look at it another way as well. All right, let's flip it. Let's look at the back. Okay. The null and alternative hypotheses are given below. Describe a type 1 false positive and type 2 false negative error. So again, I'm going to keep with my little system with the arrows. So go like this, and then go like this. All right, so in the context of the problem, describe a type 1 error, false positive. Okay, so we're saying this is the truth. This is what we actually found. So you do not actually have a disease, but the tests find that you do. So you do not have a disease, but the tests find that you do. Okay, what about a type 2 error? So this would be a false negative. So we're saying this is the truth, but this is what we found. So here we're saying you do actually have the disease. Okay, but the tests find that you don't. Okay, so right there, I'm just explaining what it would look like. So if I go back to my type 1 error, the false positive, you do not have the disease, but the tests find that you do. Well, what could that lead to? What could this issue actually lead to? Well, I'm sure a lot of stress, right? Because it's telling you that you have it, but you don't, right? So a lot of stress, mental anguish, right? Unnecessary mental suffering, and you'd probably seek out a second opinion. You would hopefully check out a second opinion. Okay. How about a type 2 error? So that false negative. So you do have the disease, but the tests find that you don't. So what would happen here? Well, you'd probably continue to get sick. You'd get sicker and sicker until you have to go back to the doctor. Right, so in both cases, right, it's not ideal, right? You're just thinking about what would be more serious in the context of the situation. We don't want either type of error, right? But we definitely want to minimize, especially here, we don't want someone to get sick or potentially die, right? And realize that the sicker they get, well, they must go back to the doctor to figure out that it was a false negative. All right, couple more examples. So occasionally, warning flares fail to ignite. A consumer advocacy group is to investigate a claim against a manufacturer of flares brought in by a person who claims that the proportion of defectives is much higher than the proportion of